Welcome back to our last lesson of Unit 2 of the Overview module, Module 1, in our study of the fundamentals of operating systems, based on the textbook Operating Systems Concepts by Abraham Silberschatz, Greg Geckney, and Peter B. Galvin. Let's pick up where we left off.
We've already seen that the original Unix system had a monolithic structure. As Unix expanded, the kernel became large and difficult to manage. In the mid-1980s, researchers at Carnegie Mellon University developed an operating system called Mach, M-A-C-H, Mach, that modularized the kernel using the microkernel approach. This method structures the operating system by removing all non-essential components from the kernel and implementing them as user-level programs that reside in separate address spaces. The result is a smaller kernel. There's not much agreement regarding which services should remain in the kernel and which should be implemented in user space, though. Typically, however, microkernels provide minimal process and memory management, in addition to a communication facility. This figure illustrates the architecture of a typical microkernel. The main function of the microkernel is to provide communication between the client program and the various services that are also running in user space. Communication is provided through message passing. For example, if a client wishes to access a file, it must interact with the file server. The client program and the service never interact directly. Rather, they communicate indirectly by exchanging messages with the microkernel. One benefit of the microkernel approach is that it makes extending the operating system easier. All new services are added to user space and consequently do not require modification of the kernel. When the kernel does have to be modified, the changes tend to be fewer because the microkernel is a smaller kernel. The resulting operating system is easier to port from one hardware design to another. When I say porting from one hardware design to another, I'm assuming that you are aware that an operating system is different when running on different hardware. By that I mean, for example, while Windows runs pretty much the same when working on a Mac or a PC, the two versions of Windows are not the same. You cannot install the same PC version of Windows on an Apple, or at least that's the way it once was, unless Apple has modified more than I thought. Now back to our discussion. The microkernel also provides more security and reliability since most services are running as user processes, not kernel processes. If a service fails, the rest of the operating system remains untouched. Unfortunately, the performance of microkernels can suffer due to increased system function overhead. When the two user-level services must communicate, messages must be copied between the services which reside in separate address spaces. In addition, the operating system may have to switch from one process to the next to exchange messages. The overhead involved in copying messages and switching between processes has been one of the largest impediments to the growth of the microkernel-based operating system. Perhaps the best current methodology for operating system design involves using loadable kernel modules. Here the kernel is a set of core components and can link in additional services via modules, either at boot time or during runtime. This type of design is common in modern implementations of Unix, such as Linux, MacOS, and Solaris, as well as Windows. The idea of the design is for the kernel to provide core services while other services are implemented dynamically as the kernel is running. Linking services dynamically is preferable to adding new features directly to the kernel, which would require recompiling the kernel every time a change was made. Therefore, we might build CPU scheduling and memory management algorithms directly into the kernel and then add support for different file systems by way of loadable modules. The overall result resembles a layered system in that each kernel has defined protected interfaces. But it is more flexible than a layered system because any module can call any other module. The approach is like the microkernel approach in that the primary module has only core functions and knowledge of how to load and communicate with other modules, but it is more efficient because modules do not need to invoke message passage in order to communicate. Linux uses loadable kernel modules, primarily for supporting device drivers and file systems. Loadable kernel modules can be inserted into the kernel as the system is started or during runtimes, such as when a USB device is plugged into a running machine. If the Linux kernel does not have the necessary driver, it can be dynamically loaded. Loaded kernel modules can be removed from the kernel during runtime as well. For Linux, loadable kernel modules allow a dynamic and modular kernel while maintaining the performance benefits of a monolithic system. Here you see a graphic depicting the Solaris operating system, showing how the kernel and the modules are related. In practice, very few operating systems adopt a single, strictly defined structure. Instead, they combine different structures, resulting in hybrid systems that address performance, security, and usability issues. For example, Linux is monolithic because having the operating system in a single address space provides very efficient performance. However, it is also modular so that new functionality can be dynamically added to the kernel. Windows is largely monolithic as well, again primarily for performance reasons, but it retains some behavior typical of microkernel systems, including providing support for separate subsystems that run as user mode processes. Windows systems also provide support for dynamically loadable kernel modules. Let's look at the structure of three hybrid systems: the Apple MacOS operating system and the two most prominent mobile systems, iOS and Android. Apple's macOS operating system is designed to run primarily on desktop and laptop computer systems, whereas iOS is a mobile operating system designed for the iPhone and the iPad tablet computer. Architecturally, macOS and iOS have a lot in common. Highlights of the various layers include the following. The user experience is similar. This layer defines a software interface that allows users to interact with computing devices. macOS uses the Aqua user interface, which is designed for a mouse and trackpad, while iOS uses the Springboard user interface, which is designed for touch devices. Also, the application frameworks layer are similar. This includes the Cocoa and Cocoa Touch frameworks, which provide the application programming interface for the Objective-C and Swift programming languages. The primary difference between Cocoa and Cocoa Touch is that Cocoa is used for developing macOS applications, and Cocoa Touch is used by iOS to provide support for hardware features unique to mobile devices such as touchscreens. Core frameworks are similar. This layer defines frameworks that support graphics and media, including QuickTime and OpenGL. Kernel environment similar. This environment, also known as Darwin, includes the Mach microkernel and the Berkeley software distribution BSD Unix kernel. As shown in this figure, applications can be designed to take advantage of user experience features to bypass them or interact directly with either the application framework or the core framework. Additionally, an application can forego frameworks entirely and communicate directly with the kernel. Some significant distinctions between macOS and iOS include the following. Because macOS is intended for desktop or laptop computers, it is compiled to run on Intel architectures. iOS is designed for mobile devices and therefore is compiled for ARM-based architectures. Those are reduced instruction set architectures. Similarly, the iOS kernel has been modified somewhat to address specific features and needs of mobile systems, such as power management and aggressive memory management. Additionally, iOS has more stringent security settings than macOS. The iOS operating system is generally much more restricted to developers than macOS, and may even be closed to developers. The Android operating system was designed by the Open Handset Alliance, which was led primarily by Google, and was developed for Android smartphones and tablet computers. While the iOS is designed to run on Apple mobile devices and is closed-sourced, Android runs on a variety of mobile platforms and is open source, which partly explains its rapid rise in popularity. Android is a lot like iOS in that it is a layered stack of software that offers a set of frameworks supporting graphics and audio and hardware features. These features in turn provide a platform for developing mobile applications that run on a bunch of Android-enabled devices. Software designers for Android devices develop applications in the Java language, but they don't normally use the standard Java API. Google has designed a separate Android API for Java development. Java applications are compiled into a form that can execute on the Android runtime, ART. This is a virtual machine designed for Android and optimized for mobile devices with limited memory and CPU processing capabilities. The structure of Android is shown in this figure. At the bottom of the Android software stack is the Linux kernel. Google has modified the Linux kernel used by Android in a variety of areas to support the special needs of mobile systems, such as power management. Take a look at the link shown here for more very good information on the Android architecture. While you're on the website, make sure you familiarize yourself with DEX files, ART, AOT, JIT, and AJL. Well, this concludes Module 1, our course overview. Next, we begin our in-depth examination of the various operating system management systems, beginning with the process management system. So take a break, look over your notes, take care of any assignments or other work you have to do, and come on back when you're ready to begin to really learn what's going on with an operating system.